Okay, so before the workshop begins, I would like to inform you that this session will be recorded and uploaded to be publicly available. So if you do not want to be visible in the recording, please turn off the webcam. And yes, having said that, I would like to welcome you from my side to the workshop on surrogate-based optimization and parallel scalable deep learning for turbulent boundary layer flows. My name is Fabian Hübenthal. I'm from the Institute of Aerodynamics at the RWTH Aachen in Germany. And together with my project partners, Iray from the Forschungszentrum Jülich and Rakesh, also from the Forschungszentrum Jülich, we want to introduce you to the topic of circuit-based optimization and parallel scalable deep learning. And this is exemplified by the use case of active drag reduction. Okay, first of all, I'd like to show you the agenda of the workshop. We are starting with the introduction and of the use case. So this will take about 10 minutes. Then I'd like to talk about the circuit-based optimization part of that workshop. And this is followed by the deep learning-based analysis, which is held by Rakesh, so about 30 minutes. And then it's followed by the high-performance computing part, which is targeting the hardware and the software as well. And the workshop itself is rounded up with the live demo session and the Q&A session at the end. On the right-hand side, you can see the speakers of the talk, and yes. With that, I'd like to start with the introduction of the use case and the use case example specifically. And here the agenda of the introduction. First of all, the project landscape of CoE Race, which I want to introduce to you. And of course, the motivation of the use case itself and the main fields of research. Starting with the project landscape of CoE Race. CoE Race itself, it's coordinated by the Forschungszentrum Jülich. CoE stands for the Center of Excellence. And the acronym RACE itself stands for Research on AI and Simulation-Based Engineering at Exascale. So just to give you the information of what Exascale means, so it's simply the floating point operations we can perform per second in the order of 10 to 18, sorry. And this project is funded by the EU in the scope of the Horizon 2020 program. And to have a reference, so the famous HPC clusters we have so far in Europe are the LUMI system in Finland, for example, which is below the Exascale at the moment, and the Joules HPC center in Germany, which is about 85 petaflops. And the goals for the CoE Race project itself, which is running through the until the end of this year, is to develop novel scalable AI and HPC methods towards Exascale, and the focus is placed on applications in the engineering and in the natural sciences. So with that having said, the use case we are focusing on is placed inside of the landscape of the use case itself. So it's inside of the compute-driven use cases. And specifically, it's the task 3.1, which is dealing with AI for turbulent boundary layer flows. Continuing with the motivation of the use case. The motivation is located in the aviation sector. That means we have to face some emissions from the aviation sectors, like the statistics are stated here on the slide. And this is including the greenhouse gases like CO2, also water vapor and soot at high altitude, and nitrogen oxides. And of course, we are facing, after the pandemic of the last years, an increasing demand of aviation, and at the same time growing costs of energy. And that's one of the most important factors, of course, the increasingly urgent climate and sustainability goals we want to satisfy. And this is, of course, a challenge. So these are some contradictory goals we want to achieve. And when having a look at the aviation itself, that means what are the main contributors to the friction? We can see that the friction drag itself is almost or more than 50% of the overall drag which the airplane is encountering. That means we want to develop some active drag reduction techniques to achieve a net power saving to improve further the fuel efficiency and the energy efficiency at the end. On this slide, you can see one of the airfoil sections we analyzed. So this is especially the geometry which is stated on the right-hand side. And you can extract the information for the flow conditions and the angle of the attack and so on, also from the right-hand side. When having a look at the airflow section itself, you can see the inflow here on that side, which is simply U infinity. And when starting the animation, you can see now how the actuation of the surface, which is going into the spanwise direction, is applied on the airflow section itself. And for visualizing the structures of the flow itself, the lambda-2 criterion is used. On the right side, upper right side, you can see the drag reduction value, so the normalized drag reduction value for the reference case, which is the black solid line, and the white line indicates the drag reduction value when using the actuation. And having to conclude, we can see that almost about 10% of drag reduction can be achieved by just using that spanwise traveling waves. Comparing the active versus the passive drag reduction techniques, we can see here on the left-hand side one example of the active ones, and on the right-hand side the riblets for the passive techniques. We can conclude the following advantages and disadvantages of these techniques. So, for example, for the active drag reduction techniques, they are flexible to flow conditions. In principle and under laboratory conditions, they achieve higher drag reduction values and net power savings. But we have to think about the power input and the technological overhead we have to spend to achieve these higher drag reduction values. And that means that at the moment, because it's not that researched as like the active passive drag reduction techniques, there's a low technological readiness level we have to face. That means at the same time, we do need more basic research to progress towards applied research in that field of active drag reduction. To conclude, the main goals of researching these techniques is the short-term vision is to understand the mechanism of drag reduction, especially of that kind of drag reduction we are analyzing here. And we want to optimize the design choices which are behind this method. The midterm vision is to design and optimize alternative, more promising active drag reduction techniques. And the long-term vision, of course, is to progress towards the application, for example, in airplanes in cruise flight, or even for high-speed trains. And at that point, I'd like to stress that this is actually basic research we are conducting here at the moment. Now I'd like to progress towards the main fields of research in the side of theory rays. And this is kind of the landscape of our research. First of all, on the left-hand side, you can see the challenges and the opportunities which are coming with that research. First of all, we have to perform well-resolved turbulent large-eddy simulations, which are expensive. And the main question is, how can we reduce the computational costs? And of course, the first approaches are using like something which is an approximation like the flat plate, and something which is related to the CFD solver itself, which is highly parallelized and efficient at using the CPU cores and the memory and so on. And we want to use AI/ML methods as stated below. And there are three main opportunities or challenges we face, which is the vast design and sparse average data space. That means, how do we choose the actuation parameters to certain flow conditions, like which are specified by the Mach number and the Reynolds number? And this is targeted by using circuit-based optimization. On the other hand, we're analyzing turbulent flows. That means there's definitely non-linearity and complexity involved. And we want to understand how, for example, the active drag reduction is influencing that flow over the airfoil, for example. And for that purpose, we use data-driven explanatory analysis techniques. For the third point, when conducting these analyses, we produce a lot of information, which is called in that on that slide a byproduct of spatially and temporally resolved data. And the question is, how can we use that storage-intensive data with these ML plus HPC, so high-performance computing methods? And for that purpose, we are focusing on the deep learning-based analysis. Now I'd like to highlight that this workshop is mainly focused on the circuit-based optimization and the deep learning-based analysis part. And the main conclusions we have drawn from the data-driven explanatory analysis are that the actuated turbulent flow is definitely a broadband problem. So that means even the small scales influence also the larger scales, and that the actuation itself is significantly influencing the inner-outer layer interaction. So that is something we have to keep in mind, and that we definitely have to conduct these well-resolved large-eddy simulations, which are expensive. With that, I'd like to go further to the second part of the workshop, which is focusing on the circuit-based optimization. Here, a short agenda of the introduction, respectively for the circuit-based optimization part. First of all, I'd like to state the original optimization problem we want to solve. Then I'm going to the introduction to the circuit-based optimization strategy in general, which means introducing the term exploitative and explorative circuit-based optimization. Then it's followed by two examples. So the first example is dealing with the support vector regression-based ridgeline optimization. And the second part is focusing on the Gaussian process regression-based Bayesian optimization part. So this is somehow showing you the pipeline approach versus the loop approach. And at the end, I'd like to close the workshop part of circuit-based optimization with a summary and outlook. Starting with the original optimization problem. First of all, we have to define what are our optimization targets. For example, this could be something like the aerodynamic coefficients, like, for example, drag, or the efficiency, like the lift-drag ratio, and so on. And in our case, we are focusing on specifically the drag reduction coefficient, which is called delta CD, which is simply the difference between the reference case and the actuated case, normalized. And we can see here two of these geometries we have analyzed. This is one on the one hand, the flat plate, and on the other hand, the airfoil section. Secondly, we are conducting something which is called active drag reduction. That means we have to put energy into the system to have this actuation going on. And the question is, what can we achieve? What is the net power saving? What is the net usage we can get out of that technique? And this is quantified by calculating the delta P net, which is the net power saving. So this is just highlighting the objectives we want to optimize. Optimizing in that case means we want to maximize these values. The second part is, what are the variables we want to optimize? In focusing on the technique we are using here, these are the spanwise traveling transversal wave actuation of the wall, which is stated in this equation stated here on the slide. And just for giving you the background of this scaling we are using, these are just the normalized values of the Cartesian coordinates, like x, y, and z, using the friction velocity and the kinematic viscosity, and the actuation parameters, which are the amplitude, the wavelength, and the period. They are normalized using these values as well. On the right-hand side, you can see the domain, which is here stated for the flat plate case. And you can see how the wave is progressing towards the spanwise direction. That means we do have these actuation parameters. In this case, these are 3. And we do have flow conditions, which are specified by the Reynolds and the Mach number. And the Reynolds number in that case for the flat plate is based on the boundary layer thickness, theta. To highlight that, so our optimization variables are actually these lambda, T, and A, which means the wavelength, the period, and the amplitude. And this factor G is just simply used for getting a smooth spatial and temporal transition between the unactuated and the actuated area. To summarize all of these information, so that means the objective and the optimization variables, we can state the following problem. Given the flow conditions, like the Reynolds number, Mach number, angle of attack for the airfoil case, the task is to choose lambda, T, and A such that the drag reduction and the net power savings are maximized. While, for example, for the airfoil case, the aerodynamic properties are not negatively affected, like the lift to drag ratio. To generalize that problem, we do have parameters P, which are collecting the Reynolds number, the Mach number, and the angle of attack. and of course the geometry we are analyzing here. The optimization variables are collected in X, which are just the actuation parameters. The feasible set is in the following talk abbreviated as this calligraphic X. And the objectives are the delta CD, which is the drag reduction we achieved, and the net power savings. To conclude, the actual optimization problem we want to solve is simply that one. So find the best actuation parameters which are maximizing one of these objectives, which are the drag reduction and the net power savings. On this slide, I'd like to show you some preliminary CFD results and the modeling data we use, for example, for the different parts which are following, like the deep learning part and so on. And we can see here on the left-hand side the flat plate results, and on the right-hand side the airfoil case results. When focusing, for example, only on the drag reduction itself, we can see that we can achieve for the flat plate something around 26% of drag reduction. And that's something we have to keep in mind. We have to spend a lot of more energy than we can save by just reducing the drag. So that means we spend 20% more of energy. But when focusing on the net power savings only, the drag reduction value is slightly less, so it's just 60%, but we could save around 10% of the energy. So that means, by concluding, that these CFD results have shown the numerical potential of that method, but we have to keep in mind that some of these objectives, so the drag reduction and the net power savings, are partially conflicting. And there are some other challenges which come up with that. Is the well-resolved LESs at HPC scale are very expensive. So we do have sparse data, and the design space itself, so the actuation parameters and analyzing the flow conditions, that's a vast design space, and we have to think about how to optimize it. And that's the motivation why we want to use circuit-based optimization at that step. Now I'd like to give you the introduction to the circuit-based optimization strategies in general. Starting with that problem, so we want to introduce a surrogate model, which uses the data, which are the LES simulations from the past. And we want to use also the prior knowledge to approximate or even replace the expansive to evaluate objective, which is based on the CFD simulations, and the feasible set and all the additional constraints which can be put on that optimization problem. So in simple words, the expansive CFD-based objective, here in our case, the well-resolved LESs, are replaced by cheap data-driven circuit machine learning models like support vector regression or Gaussian process regression. The main goal of that is to perform as few expansive sequential large-eddy simulations, LESs at HPC scale, as possible, while providing sufficiently many insightful data for understanding the problem and guiding the design choices and using a surrogate model for example, planning these simulations. And the idealized goal for the sequential optimization, which this technique is part of, is to, when having performed a lot of these simulations, that the value we get out at the end is very close to the actual optimum we are searching for. The main key arguments for using a surrogate model are that these surrogate models are capable of interpolating the data and to some extent extrapolating the data by using the prior knowledge. This is very important, especially when focusing on the extrapolation part. The second part is it's cheaper to evaluate than the original model, and it might provide further information like the prediction uncertainties or even gradients and so on. But we have to be careful in that point. It needs to be a good model to achieve, for example, the idealized goal that the value we get out at the end is very close to the actual optimum. And in the following talk, we are talking about two approaches. The first approach is something like a pipeline approach, which is ridgeline optimization. In that case, we are conducting some CFD simulations. Then we do initial setup of the surrogate model, and we exploit that surrogate model. On the other hand, we can use a loop approach, for example, Bayesian optimization, which is iteratively updating the surrogate model to conduct further simulations in a loop approach. To sum up all of these information, we started with the original optimization problem, stated here. Then we perform a kind of exploitative circuit-based optimization. So we are actually exploiting the surrogate model, and the changes of the original optimization problem are highlighted with these squares. blue squares. And going one step further, we want to close the optimization loop. And for that purpose, we are using a so-called auxiliary surrogate-based optimization problem, which is not directly using the surrogate model, but the surrogate model is incorporated in something which is called the utility or acquisition function alpha, which can have something like further hyperparameters we have to tune. And for both of them, I would like to provide you some basic information how it works. And starting with the first approach, which is the pipeline approach. This is based on support vector regression and specifically is called ridgeline optimization. So we have seen that the data consists of many of these LES simulations for plate. In that case, these are 71 of these well-resolved flat plate simulations. So that means one reference case and 70 actuated cases. The feasible set is defined as follows, and the parameters and so on. At that point, we like to focus on the drag reduction itself first. And the prior knowledge we gained from, for example, using the support vector regression is that for each lambda plus, which is the wavelength of the actuation, it features a single optimum for the drag reduction value, which is called a ridgeline. On the right-hand side, you can see how the ridgeline is progressing towards the feasible set. This is simply this solid line here. And this is the location of all the optima we have located or identified in the feasible set. Furthermore, in the literature, we know that there's something valid like, which is called the Tomiyama-Fukagata scaling, which is on the next slide introduced in more detail. And we want to use something we identified by using SVR, which is the self-similarity with respect to the wavelength. Furthermore, one of the preliminary results we can take from that simple regression is that we do have unexplored optimization potential, especially for larger wavelengths. Going further to the surrogate model itself, so the final surrogate model, which is called F hat, is approximating the drag reduction value for interpolation and extrapolation purposes. And based on the smooth interpolation results using the SVR model and the prior knowledge, like the Tomiyama-Fukagata scaling and the self-similarity, we performed sparse nonlinear symbolic regression to increase the extrapolation capabilities. Here in that slide, you can see how the self-similar approach is written down. So it's simply a factorization of the drag reduction value on the ridgeline, which is this small index R standing for, and something which is called a shape function. So the next question is, how do we approximate these two functions? And for example, for the value of the drag reduction on the ridgeline, we use the Tomiyama-Fukagata scaling, which is approximately valid on the ridgeline, and we can see how it's formulated. So the actual Fukagata scaling is written down here. This is this part, and the drag reduction value is somehow linearly depending on that value. For the ridgeline coordinates and for the shape function, we use something. Yes, here we can see how it's connected, and on the ridgeline, extrapolation is done by using these expressions, and the off-ridgeline extrapolation is done by using the shape function. So this is the main purpose of the shape function. And all of these expressions are obtained by using sparse nonlinear symbolic regression, which is similar to what is used, for example, in the Cindy algorithm by Steve L. Brandon. So to give you some validation results, we performed further simulations. So this cube here is highlighting the feasible set. So for the initial data set we had, and we can see outside of this region, we performed some simulations, which are on the ridgeline and off the ridgeline. And these points are also listed here in the table. And C is standing for the best data point we have in the data set, given these actuation parameters, which achieved about 26.3% of drag reduction. And for the on-ridgeline extrapolation, the model predicted something around 30% of drag reduction. And the actual LES simulation told us that it's more or less 31%, which is very close to the extrapolated value. And by comparing it to the off-ridgeline extrapolation, we can see it's even closer, but it's less than the on-ridgeline value we achieved. And by having a focus on the relative error, we can see that the model is quite good. So it's performing quite good. And yes, it's just about 2 to 1% of error we have seen there. So this is all about the validation of that method. But the problem is that this method is just a pipeline approach. It's not closing the loop. It's just a good approach when the model is already very good, but it's not telling you what simulations you have to perform the next step to get more insights, more valuable insights. For that purpose, we'd like to conduct Gaussian process regression-based Bayesian optimization. And this slide is summarizing how that works. So BO is a circuit-based sequential optimization strategy for automating these optimization loops. And it's a sequential optimizer in that case. And we can see on the right-hand side, the CFD-based objective again. And inside of the Bayesian optimizer, there are 4 components which are very important. Of course, we have to define the objective function. We have to define the circuit model, the acquisition function, and we have to solve the auxiliary problem at the end. And at each of these steps, we have to feed in some prior knowledge to solve that problem. And in our case, we use gPyTorch and BowTorch to achieve this Bayesian optimizer. And to just give you some background information why it's called Bayesian. So in the background, Bayes' theorem is used to incorporate that data and prior knowledge into the circuit model and to update, which is called the prior in Bayesian terms, to the posterior, which is actually the circuit model we want to use. And the stochastic circuit model provides not only the prediction, like the SVR model in the, from the last approach, but also the prediction uncertainty we want to leverage. And in our case, we want to use Gaussian process regression. And the acquisition function is used to formulate an auxiliary problem to solve the exploration-exploitation trade-off, which was not focused or even targeted by the pipeline approach in the past. And that's the key argument and the key idea how to automate the optimization loop. To just simply show you how it works, we can see here on that side the objective function f and some data points which are highlighted with these X's or crosses. And by using, for example, Bayesian Bayes' theorem, we can come from the prior, which is shown here in the upper part, to the posterior, which is closer to the true objective function, which is that solid line we can see on that side. And the Gaussian process regression does have some points where we can put in some prior knowledge, which are the mean function and the kernel function. And the posterior mean is something we use for the prediction, and the posterior standard deviation is what we call the prediction uncertainty at the end. And the terms exploration and exploitation are highlighted here in that example. When, for example, conducting a simulation point, which is close to the best value which the circuit model is proposing, we call it exploitation. And when conducting simulations in the area where the uncertainty is quite high, where we can gain the much knowledge, this is called exploration at that point. To sum up, the idea of the acquisition function and the principal workflow of BO, we started with the original problem, then we reformulated that problem. We not directly optimize the circuit model itself, but we use the acquisition function to trade off exploration and exploitation. That means using prediction and the uncertainty of the prediction. And the acquisition functions, there are some modeling choices we can make, like which acquisition function do we want to use? Is it something like the classical upper confidence bound or expected improvement and so on? And on that slide, I'm just focusing on the UCB acquisition function, which is stated here. So it's just a linear combination of the prediction value and the prediction uncertainty combined with that hyperparameter beta, which is the trade-off parameter between exploitation and exploration. And on the right-hand side, we can the principal workflow of the Bayesian optimization framework, starting with the objective function, adding the prior, which is the Gaussian process prior, feeding in some data points, then using Bayes' theorem to get to the posterior mean. And after that, we want to introduce the acquisition function itself, which is now here on the lower part of the plot. And then we want to optimize, which means maximize the acquisition function, which is the informativeness of, for example, the next simulation we want to perform. And in our case, it's definitely choosing that point, which is already a very good, very high value for the objective function. And we do have some uncertainty, large uncertainties in this areas as well. So that's the reason why that point is chosen at that point. And this is the next step we can see where the next queried simulation would be performed. And the idealized goal, by performing a lot of these steps, I mean, maybe 100 of these steps, we will progress towards the true optimum. And the important point is that these strategies are actually global optimization strategies, because we will not be stuck in that region here, but we also are at some points going to explore that region here as well, because the uncertainty is growing in that region. Then summing up the presentation of Gaussian process regression-based Bayesian optimization, we can I'd like to compare both strategies, which is based on the one hand on the SVR model and the GPR model on the other hand. And we can see here some isosurface plots. And each of these points is one of the LAS simulations we conducted in the past. And the isosurfaces are actually values for the drag reduction we achieved at these areas. And this line is the ridge line we have introduced earlier. And we can see how it's kind of similar, the models, so the SVR model and the GPR model, but we can also see some differences between them. The most important fact here at that point is that both of these models are not capable of to be extrapolated far beyond the initial data range, which is 3000. And we can see here the validation results, which are definitely outside of the initial data range, around of 5000. And to give a perspective for that, we can see on the right-hand side the ridgeline model, which is using the SVR model, but also the prior knowledge we fed into it. And we can see how it's capable of getting beyond the initial data range and how it's getting close to the actual drag reduction values we predicted. And with that, I'd like to give you the most important information out of these circuit-based optimization strategies. The important factor is we have to incorporate prior knowledge and successively gained knowledge, and to increase the optimization efficiency at the end. So we cannot blindly rely on the circuit model itself, but we have to definitely feed in this information. With that, I'd like to give you a summary and an outlook of that work. First of all, I started with the motivation, what we are dealing with and analyzing. This is the active drag reduction, and especially in our case, we are using spanwise traveling as transversal surface waves to save energy and to reduce emissions, for example, for the aviation and the high-speed train sector. For that purpose, for example, to address the computational costs of CFD-based based optimization, I introduced two examples of these optimization strategies, which is, first of all, the support vector regression-based ridgeline optimization, which means we want to identify a ridgeline model and exploit it. And on the other hand, we introduced the Gaussian process regression-based Bayesian optimization, which is using a Gaussian process regression prior, which prediction uncertainty is used to target the exploration-exploitation trade-off. And this is especially useful for closing the automation loop of performing these simulations in the future. And to sum up the results from the SVR-based ridgeline optimization, we have seen that these objectives are partially conflicting, and that definitely outside of our initial data range, there's unexplored optimization and automation potential. Progressing towards the Gaussian process progression-based Bayesian optimization, the work at the moment is focused on introducing or developing a framework for coupling the in-house CFD solver from our institute, which is called Maya, with different optimizers. That means choosing different acquisition functions and also the ridgeline model from the past. And we have seen by comparing these models on the last slide that it's definitely relevant that we have to incorporate the prior knowledge and the data into our BO framework, especially to get some optimization efficiency at the end. And with that, the next steps are definitely to progress towards the circuit model of the net power savings, because the talk was heavily focused on the drag reduction itself and not on the net power savings, which we are mostly interested in. But the net power savings are somehow more complicated to be modeled, because some principles like the self-similarity are not that easy to transfer from the drag reduction objective to the net power savings. So this is something we are working on. And of course, we want to introduce some more advanced approaches like learning the feasibility and to perform cost-aware or non-myopic or even Pareto Bayesian optimization. And with that, I'm finished with my talk. And the next talk is mainly focused on the deep learning-based analysis, which is held by Rakesh. And yes, with that, I thank you for your attention. And if you do have some short questions, you can feel free to ask them. I like to answer them. So. And if there are any questions, I think we can even progress to the talk of Rakesh.
Maybe we can start, or I mean, if there are questions, you are also encouraged to put it in the chat. We can address them.
Yes,
in the
definitely.
end. Yeah. Okay, I can go. Fabian, you have to stop sharing, I guess. Yeah.
So sharing is stopped.
Yeah. Can you see my slides?
Yes.
Okay. Yeah, welcome everyone. And thank you, Fabian, for the nice introduction to the Bayesian-based approach for the turbulent boundary layer problem. So I'm going to talk about the deep learning-based analysis that we have been doing in the CoE RACE project. And primarily, as Fabian explained, this is targeted towards task 3.1, which is on the turbulent boundary layer. But the methods or the techniques that I would be discussing are generic in the sense that they are applicable for multiple CFD-based applications. And yeah, in the end, I would come also towards a library that we have been developing over the last couple of years. And there we have a lot of examples on the contents of the talk that I present today. I would like to thank my collaborators here who have actively contributed to this talk. Let me change my pointer. Okay, yeah, so this is something which Fabian has already introduced. So we have these different kinds of use cases in CoE RACE, and this particular workshop is based on one of these compute-driven use cases, which is on the turbulent boundary layer flow. And just to recap what we are doing here, so basically in terms of the data set that we use for the machine learning based model, that is derived from this computational box. So as Fabian has introduced, we have this active drag reduction technique where we introduce this spanwise traveling surface waves, and these are parameterized by certain actuation parameters. So basically the data set that we have, which is also open source, by the way, is about 8.3 terabytes. And this data set is based on different set of actuation parameters. And these are basically how you define these waves, right? So basically like the amplitude, for example, or the wavelength or the period of the wave. So yeah, this data set is used to train different kinds of neural network. And just to introduce, okay, what are the avenues where machine learning or AI or deep learning can be used in CFD problems. So this is a recent review by Steve Brunton, and this graphic basically shows different kinds of domains where AI or machine learning could be used in CFD problems. So broadly speaking, we have, in terms of simulation methods for dealing with CFD problems, we have these three categories of, broadly speaking, three categories of modeling approaches. So first is the DNS, which is the most high fidelity approach, where we resolve all the scales. And then we have this intermediate approach, which is where LES is more high fidelity simulation, while RANS is a lower fidelity intermediate approach. And then we have the also reduced order modeling approaches where it is mostly data driven. So in terms of contribution of AI or machine learning for these different modeling approaches, one could say that, okay, in terms of DNS, we could think about increasing the speed of the simulations, right? I mean, accelerate the simulations. And then for these intermediate modeling approaches, for example, in our case, we are mostly concerned with LES since this task 3.1 is based, as Fabian already introduced. This is based on LES solver. So we are, for example, looking into improving the modeling. So the subgrid scale models, for example, in LES. So we are going to touch on that. And then one more thing which has recently become, not recently, but in the last 2 to 3 years, especially in the physical sciences domain, has become quite popular, are these so-called physics-informed neural networks, right? So basically, we want to increase the physical understanding of the machine learning models that we have. And for example, with explainable AI, we would like to increase the interpretability. So these are sort of the dimensions where the research of AI in CFD could contribute to. And in order to do that, we have explored various directions. And of course, as already introduced, we are focused towards achieving exascale performance, right? So we want methods which are scaling well, for example, in HPC systems. So we need a proper distributed training framework. So within our library, we are focusing on providing a collection of this. So basically, we have in the backend, we have the usual suspects in the distributed training, for example, PyTorch GDP, Horovod, HEAT, which is a Helmholtz Association-based distributed training framework, and DeepSpeed. So this is our backend. So we have this framework, this collection of frameworks to train our models, and then we have different categories of neural networks. So the first one, broadly categorizing, of course, this could be subcategorized as well. But if we talk in terms of, let's say, dimensionality reduction and generative networks, we have grouped together these examples. So we have autoencoders, for example, and variational autoencoders, and quite recently quite popular diffusion network in our library. Then we of course, transformers have been quite popular recently. So exploring the use of transformers for CFD problems is also quite interesting. So that is also something we have in, or we at least plan to have in our collection of models. And then also in physics informed approaches, in terms of physics informed approaches, we have the two broad categories of soft constrained and hard constrained approaches. So these are the collection of models as of now. But of course, as I said, this is constantly under development. So we keep updating our models based on new things that we encounter. So just to summarize for people who are from the CFD domain, so basically these two categories of models in terms of thinking from a CFD point of view could be classified into a spatial learning and a temporal learning categories. So for the first, this first collection of models, for example, with autoencoders, one could think that this helps us in terms of learning, for example, correlations in the spatial domain, right? So, for example, if we use convolutional layers, yeah, this helps us to understand or identify correlations in the spatial domain, while in case of temporal predictive networks, for example, RNNs or transformers, these are time marching in the temporal or time direction. So yeah, just to broadly classify them in CFD terminology. So I would start with autoencoders. So this is something we have worked for quite some time and also developed it quite a bit. And from our experience, this is actually quite useful for CFD-based studies. So what you can see here is, so I would just give a brief introduction for the sake of people who don't know much about autoencoders. So basically, we have on the left here a set of inputs. So you could think them in terms of, let's say, the velocity field. So these could be each of these could be a component or a slice of your velocity field. And then this section on the left-hand side, which is the so-called encoder, compresses this information contained in your variable, for example, in a velocity field, into this latent space, which is the compressed space that we are looking after. And then in between, yeah, there are, as is common in neural networks, we have some hidden layers. And there is the decoder part, which decompresses or reconstructs this the original field. So x1 and x1 hat are supposed to be the same field. It reconstructs this velocity field or whatever field you have from this latent space. So this is the broad summary of what autoencoders do. So few features. So basically, this is an unsupervised deterministic network. So what that means is your inputs and outputs are the same, right? So you want to reconstruct your whatever you provided to the network. Then what they do is compression, which I already said, but they can also be used for various other applications. Yeah, denoising, segmentation, neural in painting. So these are very popular, for example, in computer vision. Then we are concerned primarily in the latent space, right? So that's the compressed information that we have. In terms of what is used mostly as a loss function is the reconstruction loss. So that's basically your pixel-wise or pixel-wise or point-wise mean square error, for example, between the original and reconstructed images. So how we want to in the TBL case, how we want to use this is basically we want this latent space to be somehow interpretable, right? So as Fabian was explaining, we are concerned with some physical quantities, for example, the drag and net power saving, and we want the neural network to somehow give us good representations of these quantities from the latent space. So for example, if we are using autoencoders, we want them to give us a good representation of this quantity. So the objective would then be to be able to do that. So that's where we are moving. So this is what, so we did some studies in the past few months, and we have this kind of an architecture for the autoencoder that we have for the turbulent boundary layer problem. So on the top is the encoder part that I was referring to, and the bottom is the decoder part that we have. And this basically we have these 4 convolutional layers. There are few parameters here. So we do convolution followed by batch normalization and activation. So this is quite standard in machine learning or neural network terminology. Then we are concerned with this latent space, right? I mean, that's the part which contains the compressed information that we have. Then, okay, so this network is known as, for us, it's known as the CAENN. So that stands for convolutional autoencoder neural network. And then we combine this to this so-called regression or this prediction network. That's what PN stands for. So what it does is basically it takes the output of this this network on the left-hand side, and it goes through a few more convolutional layers, which are then flattened to followed by some fully connected layers. And then we want the dependence of the network on the extraction parameters, right? So that's what how we introduce the problems. Because basically we have a dependence of this parameters, which are the drag and net power saving on the extraction parameters. So we feed them as inputs to the network, and hope that we get good reconstructions from there. So how we train this, since as you can see, we have these two networks now, which are coupled. So first of all, we train the CAE-NN section of the network, so which is this part. So the velocity field which are used as input to the CAE-PN network. Basically we don't want to train this before, so that's a practice which helped us to get satisfactory results, which is not mentioned here. Once this network is trained, we train the rest of the network, which you see here, and then we derive two different networks for these two quantities, which you basically for the drag reduction we do a gradient masking, and the same for the net power saving, and which gives us two different networks. And basically once we have the trained network, we would test them differently. So we would the decoder part of the CANN would give us the reconstructed velocity fields, and then we would use either of these networks to reconstruct our required quantities. So to quickly look at some results that we have. So what you see here are the cross sections of the scale streamwise and spanwise velocity fields, which are compared with on the left with the LES input and the output from the CAE, and similarly for the other components. So as you can see, they provide us quite good qualitative agreement. Then we also look at something called mode decomposition. So we use a certain method developed by our colleagues at Aachen, which is called noise-assisted multivariate empirical mode decomposition. So basically, it gives us the so-called scale-specific accuracy. So it divides or decomposes the flow field into the different structures that exist. So going from large to the smaller scales. And then this helps us to compare, okay, how basically the neural network is behaving, right? I mean, how it's whether it's able to reconstruct all the scales properly. So from this analysis, what we see is, as is expected, neural networks, they are good at at least generalizable neural networks. They predict the mean features better compared to the, let's say, the small scale features. And so for IMF5 is basically corresponds to one of these, corresponds to the larger scales for which the reconstructions are quite good, while for the small scales, they denoted by IMF1, they are sort of not that good, but reconstructing certain sections only in the of these small scale features. So to look at some results for the drag and net power saving. So in general, this from this table, what you can see is also reiterates what Fabian was referring to in terms of the difficulty in reproducing the net power saving. So what you see is the testing of the model for both in terms of both interpolation and extrapolation abilities. By interpolation and extrapolation, I mean the interpolation, for example, in the extraction parameters that we have. So in general, what we see is for the drag reduction, we have quite good agreement from the neural network. but when we try to extrapolate, the net power saving network is not so good. So that's kind of the conclusion which we derive from this study. Now in the next phase, we are which is work under development, we are combining these two transformers. So the idea here is to use this compressed latent space to reconstruct or to time march our flow fields, so the velocity fields in the latent space. And for that, we are using transformers, which is sort of the obvious choice, at least in terms of how they are able to do highly nonlinear stuff properly. So that is work in progress. Hopefully in the next few weeks, we will have some of these results for you. And the next category which I would jump into are these super resolution networks. So what the objective of this part is to do wall model alias. So by wall model alias, what it means is we still have some kind of surrogate models or subgrid scale models for modeling the flow in near the wall. So we want to somehow use machine learning for doing this part, right? So since this part is the approximate part which happens in the wall model alias, we want to use machine learning to improve our approximations here. In order to do that, we looked at different generative networks, and here, for example, GANs is quite popular and a relatively older method which is used in the generative field. And autoencoders are also could also be, for example, used for super resolution. But the talk today here focuses on this last model, which are diffusion models. So diffusion models have been quite popular in the last 2 years or 3 years. So mostly in the computer vision field. Just to introduce you to what they do. So very broadly speaking, so this is an example of a computer vision task. So basically on the left, you see an image here, which is the original image denoted by x0. And there are two steps in the diffusion model. So you have the forward diffusion part and the reverse diffusion. So in the forward diffusion part, you go from x0 to x capital T, x hyphen underscore capital T. So what it means is you progressively increase the noise in the image. So basically you add some small amount of Gaussian noise iteratively to your original image. And so if you keep on increasing this, at some point you end up with isotropic Gaussian noise, as you can see this image. And so these steps are controlled. So basically there is sort of a variance scheduler which enables the prescription of what kind of noise or how much noise is added in each step. And once we arrive at this highly noised image, one would like to reconstruct, let's say, this original image from this noised image, right? So then we need to do that. So that is done with this reverse diffusion process, but this reverse diffusion process is not directly interactable. So there needs to be some sort of approximation which is done with this probability this conditional probability distribution, which is basically the conditional distribution of a time step t minus 1 given time t. So you go like sequentially back in time. And so in case of computer vision task where this Gaussian noise is known, so basically you have a closed form expression for this. One could, if this conditional is conditioned on the initial state of the image, then we have a we can have a closed formed solution for this process. But in case of CFD, that's not the case. So I would explain why in our case. So in order to do something similar for the CFD case, we introduced this so-called convolutional defiltering model that we call. So what it does is basically, instead of noise, we introduce filters. So our aim here, or objective here, is to use this for LES LES filters to basically simulate or mimic LES filters. So we similar to the diffusion process, we introduce filters of increasing width. So we start at t equal to 1 with a smaller filter width, and progressively increase the width of the filters, the size of the filter. And also we add a small noise as a regularization to this expression. And then for the reconstruction, or the reverse diffusion as it is called, process, we use a 3D unit architecture, which in the end gives us approximately the original Z that we want to obtain. And just to show you how the training process grows here, so what you can see is the loss here of different training cycles. So each of these training cycles which goes down here corresponds to a certain filter width. So once we arrive at a certain threshold error, we increase the filter width and basically repeat the process over again. As you can see, for larger values of n, so basically larger filter width, the convergence becomes slower and we need more number of epochs. So this entire process is quite computationally intensive. So as you can see, the results that I'm going to show you now are required about 10 days of training. So yeah, this is quite expensive. Just to see how these images look like after increasing the filter width. So this is the original image, and as we increase the filter width, you can see the image becomes more and more distorted. So that's the streamwise velocity that we are looking at. So to see a few results, so this is the reconstructed normalized streamwise velocity. So in this case, it is the original image. That's the filtered input to the CDM model, and then there's the output. As you can see, the CDM model is able to reconstruct the original field quite well for filter widths up to n equal to 5. Similarly, that's the streamwise velocity gradient, where also the percentage error is quite good, which is actually quite a critical component for CFD problems, as you know. So as I said, we want to use this for the wall modeled LES. So how we intend to do that? So that is work in progress that we are currently doing. So basically, just to give you a pictorial representation of how this would be done in practice. So what is shown here is a simple 2x2 grid where we assign this phi tilde. So that would be, for example, one of your variables, let's say the velocity field. So on this 2x2 grid, we prescribe the same this phi tilde on all the grid points, and then we use the CDM model to give us to have a super resolution of these variables, which gives us this reconstructed field. And from this reconstructed field, we can, for example, compute our turbulent shear stresses, for example, which can then be used in our wall model. So that's the loop connecting the solver, which runs on the CPU, and the machine learning or the inference part, which runs on the GPU. So in order to do that, we have a coupling library, which Eray would be talking more about in his talk. So that's the current work in progress. So to quickly talk to you about my final part on the physics-informed neural network. So as I said, we have these two broad categories of soft constraint and hard constraint networks. And as many of you probably know, PINS basically has considers has physical information basically in its in the network, and primarily in if we categorize these information, this could come for example in the form of residuals. For example, the Navier-Stokes equation, for example, would be written in a residual form, which go into the PINS into the loss function. And there is, of course, the prediction loss, which is the pointwise difference between the original and the reconstructed fields. And then there are the loss arising from the initial and boundary conditions, right? So these are basically the terminologies that we have. So we tested this method for a lot of problems, for example, in the CDM case, and also for some other simpler flow cases, for example, for potential flow around the cylinder, and compared these the performance of both the deep neural network, so basically the network which does not contain these physical loss terms, and the PINS network which contains the physical loss terms. So for the CDM, at least what we observed is the inclusion of this of the physical loss did not improve our estimations of the velocity field. While for the potential flow case, we did some studies, and in this case, the PINS did give us some minor improvement over the DNN case, but this still is for us, as from our experience, we would say that this is still quite challenging to do. So it's not quite generalizable, at least for problems that are of interest to us. This has not yet offered us that many advantages. And finally, on the hard constraint network, which is also quite interesting in terms of in terms of the fact that it includes this physical information inside the network itself. So in the spirit of the time, I would not go into the details here, but basically we impose the boundary conditions and the computation of the derivatives inside the network here. But also in this case, so this is inspired by this reference here. Also in this case, we see that the network without this physical constraint actually performs better, at least until now. So this is work in progress, I would say. So to summarize all of these networks, these are contained in this AI for HPC library, which is going to be introduced by Eray Enak in this talk, and also there would be a hands-on or a live demo on this. So to conclude my section on the deep learning part, so basically we have explored different machine learning algorithms or methods for different kinds of CFD problems, and our conclusion is that the autoencoders are of course very relevant for CFD fields, CFD problems, and then for super resolution is something which we think would be quite useful for improving the approximate while modeling approaches. And finally, on PINS, which is quite promising, or at least quite physically intuitive for CFD domains, it is something we are investigating, but I think there are still quite challenges remaining. So with that, I conclude my part. Since I already exceeded my time, I would hand over to Eray, and then you can maybe ask questions in the chat if there are any, and we can address them during this at the end. Yeah. So Eray, please go ahead.
Yeah, thank you, Rakesh. We have like 50 minutes left, so I will try to go as quickly as possible so we have some Q&A at the end. No, this is the wrong one. Do you see my screen?
Yes.
So we have been talking about a lot of theory until now. So I would like to talk about some practical parts that we were working on, especially related to the HPC and hardware and software, what was used on this task. My name is Eray. Thank you for coming. Let's quickly go through the same slide that we have already seen from Fabian's presentation. So objectives of RACE. Is this blocking? 1 second. Yeah. So we have this exponential increase of data, and we had these tasks: development of AI methods towards Exascale, connect and hardware infrastructures. And the last part that I would like to focus on this task is the create a unique AI framework for academia and industry. For this purpose, we have a lot of sub frameworks. The two frameworks that you can see is AI for HPC and Fidel. They are pretty much available that you can just pull and run. So let's talk about first the hardwares that we have access in this project. So you see a lot of HPCs. All the rows are a different HPC in various locations. So we have Eureka in here. We have, for instance, Mare Nostrum 4 from Barcelona and Lumi. And you see we have access to a lot of CPUs and a lot of GPUs, and how to use this kind of resources and how to go from here to an Exascale system. So, of course, we need an aim for that. In past 3.1, we started doing some initial runs, and we have seen that each epoch took really, really long time, and we need a lot of epochs to finish one training. In one GPU and Eureka DC, it would take 2 hours per epoch, for instance, for a autoencoder training. And we had to cut this somehow. Plus, we had to do some for runs for the hyperparameter tuning, some of the parameters that are needed for the tuning, which requires repeating of this process, which would take years. So what's the solution? We need to reduce the run times with the help of HPCs. So, but where to start is the question. That's why I would like to introduce you AI for HPC. Imagine that we have a triangle of CFD, AI, and HPC, where you have a CFD framework or CFD code or CFD case, and you are already running your code on HPC, and you want to include some AI perspectives to this framework or to your problem, even for post-processing, pre-processing, or whatever you want to do. So we have this framework that is already, you can find the link here. I will also share the link in the chat. Maybe Rakesh can do it. And what it does is actually gives you already an example how to start with it. So you see in the documentation, we have a lot of parts. And what does AI for HPC will give you is it will give you some data manipulation routines. Because normally when you go to the internet and then just see the trainings without the safety, you will see this MNIST dataset, for instance, for image recognition or whatever, for handwritten images. It's just basically these are structured data, and you don't need to worry about reading this data. But when you have a safety data, this could be unstructured, this could have weird shapes, this could have weird sizes. And we have some data manipulation routines already built in the AI for HPC. And not every machine learning architecture would work on the safety. So we have some examples as from the talks from Rakesh. And we have already seen some of them already there. And we can give you some idea what to do with your safety data set. And you can just immediately work on the safety data set and just use the architectures that we provide. Of course, most importantly, we have HPC optimization. So you have access to HPC, but if you just use a default training script from, I don't know, TensorFlow or PyTorch, it will not run on HPCs. Even if it runs, it will be very slow. I will tell you more about this later on, how much speed up we can achieve with these optimizations. Of course, we have a benchmarking suite, very important for your applications. You have like a lot of money invested on this HPC, so you want your code to run as fast as possible, and then you can just immediately use your benchmarking suite. And we have, of course, hyperparameter optimization suite, which is also very important because we have some hyperparameters that really affect the results. So the source code looks like this. This is already available, but I will come to that on our live session. Quickly showing you what kind of performance that you can achieve. We tested our benchmarking suite on the Jewels booster up to 3,600 something nodes. Sorry, this is a typo, up to 900 nodes, which is 3,600 GPUs. And we have a synthetic data, which is similar to a safety data. On the right side, you see the number of GPUs over the speed up. So from 4 GPUs, which is one node, up to 3,600, you would have a efficiency above 0.9, which is pretty good. But how do we achieve this? So we didn't want to invent a fire again. So we have identified existing frameworks that actually can do this. Sorry. And first of all, what we need to find a approach, what kind of parallelization techniques that we have. We have 2 different parallelization techniques. One of them is to distribute your model to the different GPUs. And the second one is to distribute the data to the different workers or GPUs. The second approach made more sense to us because our data set was huge and our models were not that large, so we could fit that to a single GPU. How this works, you see on the right side, there is this mini batch. So this is our turbulent boundary layer dataset. So we just distribute this dataset evenly to different GPUs, and each GPU consists of identical neural networks. They do the same approaches. So they load the batch, they do forward and backward pass, and then they compute a gradient. At the end, a host gathers all these gradients and averages them, also updates the weight. This way, because your dataset is distributed evenly to many GPUs, your training time is drastically reduced. But the problem is that because you have now this micro batches, so which means that these small batches goes to 1 GPU, the total mini batch will be the multiplication of the micro batch and the number of the GPUs. So if you have, let's say, an Exascale system with 1,000 GPUs, even though micro batch or batch size per GPU is very low, you will end up with a very high batch size at the end. And of course, we need to tune this to get better results, but I will talk about this later on. Rakesh already told you these frameworks that we have identified that could help us. And I will show you some results with these data sets, especially the TBL large, which is the full turbulent boundary layer dataset, a little over 8 terabytes. And I would like to start with like simple stuff. Let's compare the GPUs, for instance, AMD versus NVIDIA. You see, we did this test on the right side. You see the results. The red one is the AMD. This is a prototype system. And as you see, the blue one is the V100s, which is slower, or you can see like it's a 50% slower from the most right figure. And the A100s are slightly faster than the red ones. So we can easily identify that, yeah, NVIDIA is a little faster, but you see the respective relative performance from going to 2 GPUs to 32 GPUs is the same. So actually, this is the capabilities of the hardware. So we had no problem with the software, probably not with the middleware. So we were happy with that. Of course, these are just old GPUs now. The new ones are released. So we are constantly testing it. And at the moment, AI for HPC can work on both GPUs. Then we tested the frameworks. to see which framework that we would like to go on. So there are like 6 figures here. So I think the most important part is that in the first A, you see that the heat is much slower than the rest of them. So the rest of the frameworks have approximately similar computational times, but the heat is lower. Well, we found out that this framework is not perfectly utilizing all the GPUs effectively. So we immediately say that, okay, we don't have to worry about the heat, so let's focus on the rest of the 3 frameworks. And the speed up and B, you see that all these frameworks are achieving similar performance, but the training error is quite different. You see, if you ignore the green one, you see the horror word is actually having a really good training error with lower number of the GPUs. And with a lot of GPUs, deep speed and horror word are in par, but PyTorch DDP, which is actually coming default with the PyTorch library, achieves the worst training error. Before coming to this training error, let's discuss what kind of optimizations we have done. So I'm not going to repeat these things, but most importantly, we achieved 10 times the speed up. So if you just go to the website of PyTorch and pull it and then do necessary modifications of your code that runs on the HPC, you will achieve this epoch time of red line. With the optimizations that are in AI for HPC, you will have the blue line. The speed up is the same. This achievement is mostly done because of the faster data loader and reduced precision definitions. However, you see immediately here that the first image that I showed you had really good speed up. Now the AI for HPC does not have that better of speed up. We see the efficiencies are close to 0.6 now. So we of course analyzed that. And we found out that the influence of the data set and input output really affects the efficiency as expected. So what happens that even though your data seems huge, when you distribute it to a lot of GPUs, the data per GPU becomes very limited, which means that if you have really less data per GPU, there will be a communication overhead because there won't be anything to compute. So that's why we decided to test a 10 times larger data set, which is now 83 terabytes. And the first right-hand side, you see that why I'm coming to this is that from 4 GPUs to 8 GPUs, the left pie charts are the CPU processes. Input output is the yellow, red one is the operations. On the right side GPU is the yellow is the computations and the red is communication. So if you have 4 GPUs to 8 GPUs, you see nothing really changes. I mean, the computation percentage from the overall computation is the same for 4 and 8 GPUs. This is nice. But as I said, if you go like a lot of GPUs, for instance, in this case, for 64 GPUs, you see that you will not have any more operations. So because you have so less data per GPU, you will just waste time. For instance, on the right side, right bottom pie chart, you will waste a lot of time on the communication. Okay, then I come to this 83 terabyte data set. So this is what happens. The red one was the previous plot from the previous slide, and the blue one is the one with 10 times more data set. You see your efficiency improves a lot, but still it's not in the perfect level. So this means that even 83 terabyte, you can go more, to be honest. If you have an Exascale system, so this concludes that you need a really huge data set also. And of course, the important part is the mini batch size. I told you the mini batch is like micro batch times the number of GPUs. In this case, if you have 1024 GPUs, so mini batch minimum that you can have is 1024. So we did some sensitivity analysis, and we have found out that learning rate has the most sensitive to the results. So if we decided that if we modify learning rate, maybe we can cope up with this increased batch size effectively and have a good accuracy. So there are two major solutions for this mini batch size problem. Of course, the first one is the scaling the learning rate. So we just increase the learning rate. We have tested to increase the learning rate with the number of GPUs. For instance, if we have a learning rate of 1 or 0.1, with 100 GPUs, it will be 0.1 times 100. And there's also this adaptive summation algorithm. I'm just going to put you the paper. You can check the details. It's a little bit harder to implement. But what it does, your problem becomes learning rate independent. And then we both tested these two methods, and then you can see that the training error on the y-axis and the number of GPUs on the x-axis. So with a fixed learning rate, what you would have, because of this increasing mini batch size, you would go a higher training error every time you increase the number of the GPUs. So if you apply this learning rate scaling, you see that your training error is much less than the red one. And even if you pass number of the GPUs, your training error will be in similar magnitude, which is the same with the adaptive summation algorithm. So these two approaches, we were really satisfied. And I think it makes really sense, because when you go to an Exascale system, you will probably have here 6,000, 10,000 GPUs. So you don't want your training accuracy to be low. So a few remarks for the AI for HPC before I go to live demo. So we are really proud to show you the first steps to combine AI safety and HPC problems. You can immediately pull the repo and then start running if you're interested on that. We are very happy with the performance. Of course, the data size and the input-output bottlenecks are evident, but yeah, there's nothing we can do about it at the moment. We are daily improving what we can do about this. We are giving constant development and user support. If you have any questions, that's just feel free to write it to us. And we also want to say that we say that this is a CFD. Yeah, AI for HPC has the safety part, but this is actually not limited to the safety. It can be applied to any data-driven project that you have. Of course, the architecture, machine learning architecture will be different for your use case, of course. But at least the AI and HPC parts, you can just transfer this knowledge to your problem as well. Well, thank you for your attention. I can probably continue with the live demo. Yeah, 20 minutes live demo, I think it's fine. And then we can ask the general questions maybe at the end. Okay, so I hope you can see my screen. Let me close this. So this is the user documentation of the AI for HPC, a general info. This is a part of CoE Race project. If you click on this, you go to our awesome website. Maybe you're interested on the CoE Race project. You see a lot of nice images, a lot of news and stuff. Please do that if you have time. This is the same image that I showed you, and the source code is also here. I'm just gonna close that and then go to the bottom. So if we have access to an HPC, I'm not gonna go to that part. Let's see if my terminal is working. Nice. So I'm just going to connect one of the HPCs in Jülich. It's the Eureka. I'm gonna wait for it. It's gonna do some stuff. Well, it's already have a virtual environment, so I'm gonna deactivate that. I'm gonna clean the screen. I'm gonna go to my Scratch partition. And I already created this workshop folder for you. And then we can see that we can go to the installation part. It says that the only thing that you require is an HPC and a Python version of 3.10. So let's see our Python version, copy this code to the right side, 3.10.4, nice. Let's clone this repository. And then hope for the best. Yeah. Now, this is what the repository will look like at this time. So we have several folders, batch and cases folders. Batch, you will have only a configuration and a start script file here that you don't have to worry about. This is there as a base. There is a benchmarking suite that I have told you. There is cases. I will come to that. There is hyperparameter optimization. There are some helper scripts, and there's this user documentation, and there's the setup. Normally, you just write Python setup py, and then it will just generate everything for you, but this will take a lot of time. So I have done this already. So let's just copy the compiled environment to here. So we don't waste some time. And then of course we forgot this. Let's just run this code. So how to set up this? We have 8 different cases. Some of the cases that you have already seen from these slides, previous slides. For instance, the first case, which means that it uses this distributed data parallel default framework from PyTorch. This is the actuated turbulent boundary layer dataset. These are datasets we have. So we have 2 datasets, MNIST and ATBL. And we have these networks or the architectures here. So autoencoders, diffusion model, regression, normal CNN. Let's start with 1. So all you have to do is then write here case 1. Let's clean this. And then it will just compile. Of course, we have the source. Normally this, yeah. What is going on? Did I not compile this? Anyways, let's continue. So this setup will identify which HPC it is currently in. And we have at the moment just 3 HPCs, but we are working on it. So this will automatically identify if it is in UWLS, Eureka, and deepest HPCs. We are in Eureka right now. And it will generate 2 files. One is AI for HPC, which is the main training script. I will come to that. And it will also create a start script that you don't have to worry about. This you can just, this has to be submitted to the HPC. I hope you're familiar with that. But if you have an account, you just rename this account. Let me write mine. And then what it does, it will just put the job to our development partition for 15 minutes when using 1 node that has 4 GPUs. And the modules, environment, and everything is automatically being set, so you don't have to worry about it. And this start script already has this environment, the variables that is required by the HPC. Don't have to worry about that part. There's some job information, and most importantly, you have this launch part. Normally, this is very problematic on the HPC side, where the connection between the nodes are really important. PyTorch uses something called a nickel. And for that, you need to express those flags. For instance, endpoint, you have to give like the IP names of different nodes, which this small code snippet does it for you. And you also have to open a gate to it. And this is automatic, so you don't have to worry about the rest. And we have also this src file. Normally, what our intention was actually to leave this AI for HPC py, which is the main training script alone. So this has a lot of stuff in it. It is well documented, so there are a lot of commands. You can go through with it. But I would like to go to the source file. Let's close this. So we have 4 different Python files here: data loader, network, parsing, and post. Let's start with the parsing. Let's remove this. So you see we have a lot of parsable options. We have already implemented those in this AI for HPC training script. Of course, the data directory is, yeah, you need that. And you also want to write some checkpoint files because in HPCs, you will always have a limited allocation time, for instance, 1 day. At the end, you want to train maybe for 10 days, so you want to have some restarts in between. So this is actually so implemented that if the code sees that your loss function decreases considerably, it will already do a checkpoint by itself. But you will also have a control saying that I want to have a checkpoint for, let's say, every 100 epochs. This is it. We have also an option to actually multiply the dataset size. So what it does, for instance, that I showed you, you are doing a benchmark, and then your dataset is only, let's say, 50 megabyte. You can actually use this flag to multiply this 50 megabyte dataset, which has, let's say, 10 datasets in it, to 20 datasets for 1,000 datasets. But this is just for benchmarking purposes. These are model parameters. Everyone probably knows this: batch size, epochs, learning rate, the scheduler, decay, gamma. We have also a possibility to shuffle dataset every epoch, which helps because I told you the data set is being distributed to the different GPUs. But if those GPUs are seeing the same data set over and over again, well, yeah, you're losing the information from the other parts of this micro batch. So what it does, it just shuffles the data set around every epoch. A little bit IO intensive, but it's okay. Improves the accuracy. You can enable the schedulers, learning rate schedulers here. And we have also the gradient predivide factor. You can just predivide all the model gradients if you want. Then we have some debug parsers. So what if you want to just do a test run in your HPC and not waste a lot of computational time that is very valuable to you? You just do a test run. I will come to this, but normally we have also post-processing part that will give you nice plots. You can disable this if you're not interested on that. So you can do seeding, which will do a deterministic one. It will just disable all the random number generators if you're interested to achieve the same runs and over again. This is logging interval. So it will just log some data that you can check at the end every, let's say, 10 epochs or 20 epochs. Here, you can have a control on that. This is only for autoencoder. You can actually export the latent space to your liking and then just save it as an H5 file and play around with it if you want. Then we have parallel parsers. We have 3 backends. We can use MPI, very standard, or we can use the nickel that comes directly from the GPU manufacturers, or we can use the glue from Facebook, All of them perform differently on different HPC systems, so you have to try and see which one is faster. But usually MPI is like the easiest to set up. It's not the fastest, but the easiest to set up. Since all the operations are done on the GPU, you can actually use the CPUs to the data loaders, so you can fetch the data much faster than that. Because the idea is that if the GPU is idle, you are wasting a lot of resources. Just go as much as you can with this number of workers, preferably everything that you have in the CPU part. For instance, we have 128 cores in Eureka DC, so I use all of them. Prefetch factor, you don't have to play with it, but what it does that it just prefetches more data to the system memory, so it will be ready for the GPUs. The default is 2. I mean, if you don't go lower than 2, I think it's fine. You can just disable CUDA. You can use a fork server for the data loader, which is in the horror word that you need to do this, but normally you don't have to worry about this. This is also the deep speed, I guess, requires this local rank as a parser. This one that I love, these are the benchmarking parsers. For instance, you want to do a synthetic data instead of like the real, and then disable the input output IO. You just open this command, what it does is actually it will just generate on the fly some CFD-like data, which are not actual data, but the memory allocation will be the same, and it will just generate this many data samples per worker, which in the end, if you're coming from the CFD perspective, it's like a weak scaling, because every worker will have the same number of samples. But as you see, normally, if you increase the number of GPUs, you will actually have less samples per GPU. This is, in this case, like a weak scaling. This is doing a bench run. This is like with a profiler, which I think it's very important to see what kind of bottlenecks that you have. For instance, this pie charts that I prepared for you were actually requiring this bench run. This will profile everything for even every communication, data loading, everything, and then give you a nice list. And those are some optimizations like CUDNN optimizations, mixed precision. You can actually reduce the precision of the data set. This will greatly reduce the training, but yeah, if you have a safety, which you have like small and large scales at the same time, velocity scales or whatever, you wouldn't want to do this. Well, you can scale learning rate. This is nice to have this nice accuracies with the increasing number of workers. I showed you in my one of the last slides. You can accumulate the gradients. So instead of doing a backpropagation every epoch, you can do like 3, 4, 5 epochs, then do one backpropagation if you have like a communication problems. This will greatly reduce the communication overhead if you have. You can just reduce the parameters to the FP16 all instead of like automatic mixed precision. Everything will be FP16 if you have also like some issues with the communication. Here's that the summation. You can enable that. And I mean, if you enable this and enable that, the code will select this one. So don't worry about it. And there's also batch per all videos. So if you do accumulation, so gradient accumulation, the code will still try to do some MPI all gather or nickel all gather, whatever. So you can actually disable this all gather operations as well. So this one and this one goes together. So if you want to do like a backpropagation every 5 epochs, you want to skip all reduce commands for 5 epochs, which makes a lot of sense. Okay. Oh, my time is almost up. I need to hurry up. Let's go to like networks, which is quick. all these networks, let me see. So we have neural networks, convolutional neural networks, autoencoders, the 3D version of the autoencoder with the 3D convolutions, regression network, UNet, 3D UNet, the CDM model, everything is already included there. So our intention is that if you have a model, you just write it here instead of playing with AI for HPC.py, just add this one, modify this file. So nothing is broken. We can just check one of these. I mean, these are you can find it from the internet if you want, or you can just develop it yourself. For instance, this one, Rakesh developed it. Let's go to data loaders. Oh, data loaders. This is important. So this is the data manipulation part. The problem is that, of course, you have a CT data set. For instance, one of them is that you have H5 files and you want to read it to the input to the network. Here you can do that. This one reads the H5 files. Depending on the reduced dataset flag, this parsing flag that you had, it will just reduce this dataset to a different precision. But it is, as you can see, it's very easy to play around the dataset here and do all these modifications. You can do normalization. You can even use NumPy commands or torch commands. You're completely free to do whatever with your dataset. And this is a nice example. Not everything is the same. We are aware of that. That's why this is a basis. So I don't think your CFD dataset will be directly be able to use this part, but you can just easily modify it if you know a little bit of coding. Let's close that. And the last one is the post-processing, which is nothing, is just we want to gather all the post-processing routines to one part. For instance, if you want to have some scatter plots, here it is how it has been done. For instance, these Rakesh has shown some of these scatter plots. We have done it with this. Okay, like 2 minutes, I want to go to the benchmark. So there's this in benchmark and hyperparameter optimization, there are different setup files. Let's quickly run this. After you run the main setup, you can run the setup bench. You need, of course, you need an account. You just type the account of your HPC system, and then it will just generate. It will just generate this file, which is actually this benchmark is being built on top of the Stoop benchmarking suite. So here you don't have to worry about anything. All you have to do is that. So this is the number of the GPUs. You just modify this. This actually don't have to do that. We have already done it for you. But for instance, I just want to see 1 and 2 node work. And we have also the results. We have this plot benchmarking Jupyter notebook that you can immediately plot your nice benchmarking results. Jube is already installed when you install this AI for HPC. So you just run, it's in the README. You just run, maybe if I go here. I mean, everything is here. So benchmarking suite. Okay. We just do a Jube run and general job systems XML and do a small run. No files found using data there. What is going on? Oh yeah, we of course have to have a data directory. Anyways, these will run, but yeah, we are out of time. But at the end, you get a nice result, a comma separated file, which you can use this plot bench, Jupyter notebook, to generate the speed up and efficiency plots, which are all here. If you open the notebook, it will look much nicer, of course. I mean, my time is up, so I can talk years. Right, guys? Maybe I should stop.
Yeah, we can see if there are questions. There is a question, so.
Okay, so if you have more questions about this AI for HPC, let me know. Let's go to the questions. Okay. Okay, the first question, maybe I can read. I have a question about the LES super resolution CNN AE. As I understand, you blurred the velocity field, then trained the network to reconstruct the original velocity field. My intuition says that the low resolution LES simulations are qualitatively different from the high resolution sims. Do you validate low resolution upscale simulations with high resolution LES simulations? We want to validate it. That's why we are now on the state that we are creating this coupling interface to our CFD code. And we will run this trained machine learning model as an inference and then validate with the high resolution simulations. But if you're asking if the generated high resolution upscaled images are the same with the high resolution LES simulations, I think it's the same. I mean, Rakesh showed you some results. The error is less than 0.5% if you check it pixel by pixel, I hope. Oh no, you answered that. Why are you not stopping me?
Yeah, I mean, it's okay. I think it was also good to say it. Maybe you can go to the last question, which is on the AI for HPC.
Okay, I have a question regarding AI for HPC. What language is used to communicate with heterogeneous GPUs, NVIDIA and Intel? It's OpenACC, HIP, SYCL. We are using directly the communication library that's coming from the NVIDIA. Yeah, we are at the moment using the communication backend is called C10D, as you can see here. It's written in C++. More questions?
And so if there are no more questions, maybe we can give some further information about our future work. Like Ira told, the next step is to couple the Maya solver, which is the CFD solver, using Fiddle, and yeah.
I can stop sharing.
As I can see it right now, there are no more questions. And some of the people are leaving the room, so.
I think this was a nice workshop. So we can end it.
Yeah, if there are no more questions, we can end it. We will share the video with everyone on the website and social media in the next few days. Okay. Okay, thank you very much, everyone.
Thank you for joining.
Thank you.
Yes, thank you and see you.
Bye.
Bye.